we're tackling Noether's theorem.
Mm-hmm.
I mean, why are things like energy and momentum conserved? Is it just, a lucky coincidence? Or something deeper going on?
That's exactly the mystery, isn't it? And this deep dive is all about unpacking that. Noether's theorem, it doesn't just state that conservation happens.
Right.
It actually reveals this incredibly elegant reason behind it.
Mm.
So our mission, really, is to get our heads around this link, this profound connection between symmetry in the universe and the stuff that stays the same, the conserved quantities.
Yeah, it feels like one of those bedrock principles in physics. Almost sounds simple on the surface, but then, whoa, the implications are huge.
Totally. It's this unifying idea formulated by the truly brilliant mathematician Emmy Noether, over a century ago now.
Back in the 1910s.
Right. And it's still absolutely vital. I mean, for everything from basic mechanics to, like you said, cutting-edge particle physics at CERN today. It gives us a lens, really, to see the underlying structure of physical laws.
So, okay, Emmy Noether, tell us a bit about her and this core idea she developed around 1915, published 1918. What's the elevator pitch?
Where Emmy Noether was just a groundbreaking German mathematician. Her work was crucial, not just here, but across abstract algebra, general relativity, just foundational stuff.
Okay.
And her theorem, in essence, draws this direct line. It's almost like magic. For every continuous symmetry you find in a physical system's description specifically, its action, there has to be a corresponding quantity that doesn't change over time. It's conserved.
Wait, a guaranteed connection. Like if you spot a symmetry, boom, you know something's conserved.
Precisely. It's a very strict, if this symmetry exists, then this conservation law must follow. Within that mathematical framework, of course. No ifs, ands, or buts.
Okay, you mentioned a couple of key terms there. Things our listeners probably know, but let's just anchor them for this discussion. Action first. We know it from, the principle of least action, right? It's a functional.
Right, exactly. So in physics approaches like Lagrangian mechanics, the action is this value you calculate for the entire path a system takes.
Yeah.
And the principle of least action says the system naturally follows the path where that action value is, minimal, or at least stationary.
Okay.
Now, when we say the action has a symmetry, we mean you can perform some kind of smooth transformation, like shifting everything forward in time, or maybe sliding the whole setup sideways in space.
Mm-hmm.
And the mathematical form of that action, or the equations of motion you get from it, they don't change. The physics underneath is indifferent to that transformation.
So the physics stays the same even though you made some smooth change, like time passing or moving it.
Yes, exactly. It's about the invariance. The system's dynamics don't care about that specific continuous change in coordinates or fields. And conserved quantity, that's more straightforward, right?
Yeah, energy, momentum, charge,
Mm-hmm.
stuff that stays constant in an isolated system.
The total amount just doesn't change over time.
The really incredible part is how Noether showed these two things. The symmetry and the conservation are just like two sides of the same coin.
Fundamentally linked, yes.
Let's make this concrete. The sources give some great examples, maybe the most intuitive one first. Time invariance.
Okay, yeah. The symmetry here is pretty easy to grasp, I think. It's just the idea that the basic laws of physics, they don't change from Monday to Tuesday.
Right.
If you set up an experiment today, control all the conditions, get a result, and then you do the exact same experiment tomorrow, same conditions, you expect the same result, don't you?
Yeah, absolutely. Otherwise, science would be impossible.
Exactly. So the system's behavior is symmetric under translation in time. Shifting it forward or backward in time doesn't change the underlying rules.
And Noether says this symmetry under time translation maps directly to what?
Conservation of energy.
Total energy.
Whoa. Okay, so the reason energy is conserved, this fundamental law, it's not just some random cosmic rule. It's a direct consequence of the fact that the universe's operating manual doesn't change from day to day.
That's it. Precisely. The source material really nails this. It says, look, if your experiment did give different results day after day under identical conditions, well, that would mean time symmetry is broken.
And energy wouldn't be conserved anymore.
Right out the window. The consistency of physics across time forces energy conservation upon us. It's baked in.
Okay, mind slightly blown. What about moving things, like translational invariance, shifting in space?
So that connects to the idea that space is, homogeneous. The laws of physics are the same here as they are over there.
Everywhere is the same, physics-wise.
Basically, yes.
Yeah.
If you take your isolated experiment, your system, and you just pick it up and move it somewhere else without rotating it or anything.
It's fundamental physics, its action, stays the same. It's symmetric under spatial translation.
And that symmetry gives us
Conservation of linear momentum. total momentum.
Ah, okay. That makes sense. So when two billiard balls collide, their total momentum before and after is the same. Because the physics of that collision doesn't care if it happens on the left side of the table or the right side.
Exactly. If the laws of physics somehow change depending on location, then momentum conservation wouldn't hold. The uniformity of space guarantees it.
Okay, time, space. What about orientation, rotating things, rotational invariance?
Right, this relates to space being isotropic, meaning the laws of physics don't depend on which direction you're facing.
Like there's no special up direction for the laws themselves.
Precisely. So if you take your isolated system and just rotate the whole thing, the physics governing it doesn't change. It's symmetric under rotation.
Which leads directly, Noether says, to.
Conservation of angular momentum.
Okay, the spinning ice skater pulling her arms in.
That's the classic example, isn't it? She spins faster because her angular momentum has to be conserved. And that conservation comes straight from the rotational symmetry of the physics involved. Same for planets orbiting stars. Their angular momentum conservation is tied to this symmetry.
These first three feel quite intuitive, connecting space-time symmetries to everyday conservation laws. But the source also mentioned gauge symmetry. That sounds more abstract, linking to electric charge.
It definitely is more abstract, yeah. It's not about symmetries of space-time coordinates in the same direct way. It's about symmetries in how we mathematically describe fields and potentials. Think electromagnetism or quantum mechanics.
Okay.
It involves transformations you can make to the mathematical description changing potentials or the phase of a quantum wave function in a certain way that leave all the physically observable things, like forces or probabilities, completely unchanged.
So you change the math description, but the actual physics you'd measure stays identical.
Exactly. Think of it like map coordinates. You can use different coordinate systems to describe the same physical territory, right? Gauge symmetry is kind of like saying you can switch between certain mathematical maps without changing the underlying physical reality, the territory.
Huh. And Noether's theorem still applies. This more mathematical symmetry also guarantees something is conserved.
It does, absolutely. Specifically, certain types of gauge symmetry are directly linked to the conservation of associated charges.
Like electric charge.
That's the key example from the source material, yes. The fact that electric charge is conserved in every single interaction we've ever observed never just disappears or appears out of nowhere. That's a direct consequence of a specific gauge symmetry built into the laws of electromagnetism and quantum electrodynamics.
Wow. Okay. So we've got time symmetry giving energy conservation, space translation giving linear momentum, rotation giving angular momentum, and these gauge symmetries giving charge conservation. That covers a lot of fundamental physics.
It really does.
Stepping back then, beyond these killer examples, what's the really big picture here? Why is this theorem considered such a, cornerstone?
Well, it's foundational for a bunch of reasons. First, it's this incredibly powerful unifying principle. You see, before Noether, physicists knew about symmetries, and they knew about conservation laws, but they often seemed like separate facts about the world.
Just things we observed.
Right. Noether, they came along and showed, no, they are deeply intrinsically connected. There's an underlying logical structure. She gave us the why that links them. It just tied together so many disparate observations.
Okay, so it unified existing knowledge. What else?
It has amazing predictive power. Think about it. If you're a theorist cooking up a new theory of physics, and you discover your theory has some new kind of continuous symmetry hidden within it, Noether's theorem immediately tells you, hey, there must be a conserved quantity associated with that symmetry. Maybe some new kind of charge or number.
Like a tool for discovery.
Absolutely. A theoretical treasure map, as you put it earlier. And it works the other way, too. If experimentalists discover some quantity that seems to be conserved unexpectedly,
then the theorists know there must be some hidden symmetry in nature they haven't accounted for yet.
Exactly. Go find the symmetry. This is why it's such a foundation of modern physics. It's not just classical mechanics. It's crucial in quantum mechanics, general relativity, and it's absolutely central to quantum field theory, which is how we describe particle physics.
Like at CERN.
Precisely. As the source mentions, understanding the symmetries and the conserved quantum numbers they imply is fundamental to classifying particles, predicting interactions, figuring out what's allowed and what's forbidden.
So it's not just a historical artifact. It's actively used now.
Oh, constantly. And it's a key guiding principle for new theories. When physicists try to build models that go beyond our current understanding, beyond the standard model, they often start by postulating symmetries. They say, what if the universe has this extra symmetry? And then, Noether's theorem helps dictate what kind of particles and forces are allowed in that new theory, and what quantities would have to be conserved. It gives structure to the search.
Provides guardrails for building new physics?
Very much so.
Hmm.
And maybe more mundanely, but still importantly, it's just a powerful problem-solving tool. Using conservation laws simplifies calculations enormously. Instead of tracking complex forces, you just track the conserved quantities.
Makes the math easier.
A lot easier, often.
It's really quite something that this all came from Emmy Noether, especially when you think about the time she was working.
It really is. And this work, it was partly done while she was helping sort out some really tricky issues with energy conservation in Einstein's then new theory of general relativity. Her insights were just revolutionary.
And she faced so much resistance, right, as a woman in that academic world.
Huge barriers. It's a whole other story, but her perseverance and brilliance are just staggering. Her contributions are now, thankfully, recognized as truly monumental in both physics and mathematics. It really shows how powerful abstract thought can be in revealing fundamental truths about reality.
Absolutely. And what she revealed is this beautiful, deep connection that the symmetries of the universe, the things the laws don't care about, are the reasons certain quantities have to stay constant. It reframes how you think about why things are conserved.
It really does. For anyone listening who's interested in the fundamental goers of the cosmos, understanding this theorem is pretty essential. It tells you invariance dictates constancy.
What the laws are indifferent to, that's what gets conserved.
You got it.
Which actually brings us to a really fascinating final thought, something spurred by the implications in the source material. We've built this picture where conservation laws, energy, momentum seem rock solid because they stem from these fundamental symmetries of time and space being perfectly uniform.
The bedrock.
But what if? Just what if one of those symmetries wasn't perfectly perfect? What if there was some tiny, maybe usually undetectable flaw, like maybe time translation symmetry isn't quite exact under extreme conditions, or maybe space isn't perfectly isotropic everywhere?
Ooh, okay. Now that would be interesting. Extremely interesting.
Should a tiny violation like that, maybe observed in some rare astrophysical event or a super precise experiment, be the first hint of entirely new physics?
It absolutely could. It would force us to rethink those conservation laws, at least under those specific circumstances. It might suggest the symmetry isn't fundamental, or that it's broken by something we don't yet understand.
Like it could point towards hidden dimensions or new forces, or maybe even signal that space-time itself has properties we haven't grasped. Finding a crack in that symmetry
Would potentially open up a whole new landscape in physics.
Yeah.
It would tell us the universe isn't quite as, uniform or symmetric as we assumed.
makes you really ponder, doesn't it? The exquisite balance implied by these symmetries, and what even the slightest imperfection could reveal about the true nature of reality.